So on Monday we did this one perfectly inelastic. I forgot what the numbers were. Was it 3, 2? Is this one? Was it something like that?
Yeah, like that.
So we did one where they get stuck. We did perfectly inelastic. We said what's the final velocity, what's the percent loss of energy. So this is where it was stuck, and we find the final. Then we did semi-elastic. In the semi-elastic, they bounce away from each other. But the problem in the semi-elastic, the problem gives you one of the pieces of the information. So they say, let's say V2 is 0.2 meters per second. And they say find this one. And I think for that one we found out that the final velocity is 0, because whether it's semi-elastic or elastic, it's still going to conserve momentum, right? So then we're going to have, so this would be semi-elastic. And then the perfectly elastic would be in the perfectly elastic, you're going to have two unknowns, but neither of them are going to be given to you. They're going to be saying, find V1 and V2. So, perfectly elastic. So in a perfectly elastic collision, you have to conserve kinetic energy and momentum.
Right.
Right? So now the momentum conservation, momentum total initial equals momentum total final. So now we have here 5. The initial momentum was, I think, no, I don't think this is the right number. I think it was different.
You did 3.
Oh, 3,
We did 2 kilograms, 3 meters per second.
2.
2 kilograms, 3 meters per second.
Oh, okay. And then this was 3 and 2.
Yeah. Yeah, so the left one was
No, I
3.
think it was the total momentum was.
5 and 1.
Well, the right one was 5 kilograms and 1 meter per second.
Oh, okay, yeah, exactly. So I remember the initial momentum of the system was 1. So that's how I kind of remember it. So now the initial momentum is going to be 1. The final momentum is going to be 3v2 minus 5v1. So now you see you have 2 unknowns. So if you have 2 unknowns, you have to conserve something else, which then we say, well, because it's perfectly elastic, we're conserving kinetic energy. So now, then for that one, we're going to say the initial kinetic energy of the system equals to its final kinetic energy. Okay, and you're going to have, I think I can get rid of this 2. So then you're just going to have here 4 times 3, 12 plus 5. That's going to be 17. So then you can do substitution. You can say you have 2 equations, 2 unknowns, then solve for one of them here. You can say 3v2 is 1 plus 5v1, and then divide this by 3. And then substitute that into the v2 here. So 17 is equal to 5v1 squared plus 3, 1 plus 5v1 over 3 squared. So substitute, use the momentum equation to solve for one of the variables, and then plug it into the kinetic energy equation.
Why did you set momentum total initial to 1? Or
It
how
was
did-
1.
Okay.
I remember from Monday, it was 3 times 2, 5 times negative 1. So when you add them, you
Oh,
get
yeah,
6
yeah, yeah.
minus 5, which is 1. Yeah. So then you're gonna square that. Let's see, we have 17. On the bottom, you're gonna have 3 squared, which is a 9. Right? And then the 3 goes into the 9 3 times. Multiply everything by 3, so you get rid of fractions. So you're gonna get 51 is 15 v1 squared plus 1 plus 5 v1 squared. And when you expand that out, you're gonna get 51, 15 v1 squared plus, and then expand the binomial. 5 squared is 25. 25 v1 squared plus, then double their product, which is gonna be 10, right? 10 v1 plus 1. Then you're gonna have 0 is equal to 35 v1 squared plus 10 v1, 1 minus 50.
40.
What is it?
40.
Oh yeah, 40, exactly. Minus 50, right?
Yes.
Then you can get rid of the 0. Now, when you do a perfectly elastic collision, what's usually going to happen, not usually, it's actually always going to happen. You're going to end up with a quadratic equation whose one of the solutions for V1 is going to equal to the original velocity of that block, right? So if V1 is negative 1, right, that means the 5 kilogram is actually still moving to the right after the collision. So I know that this quadratic equation should be factorable, and one of the solutions should be equal to its original velocity, which is negative 1. So then we can solve for the other equation. So I always guarantee you that the equation you get will be factorable, and one of the solutions will equal to its other one, right? So now in order to make this one work, what would you need? 4v1 minus 5? Is that right?
So it should be V1 minus 1 and 4V1.
No, plus 1. It needs to become negative 1. So does that work? 4v1 squared negative 5 plus 4.
That's,
No, hold on.
yeah.
Negative 1, right?
Yeah. Yeah, that's the equation. But
Oh wait, I did something wrong here. What did I do? What did I do? I should have written here 3.
Oh.
oh,
Yeah.
I switched the blocks. It's almost like quantum mechanics. They tunnel through each other, right? The blocks just sort of passing each other. Okay, so that means let's see, how does that change things? Well, why don't I just call this V1 and V2?
yeah, that works.
Then I don't have to change this. I'm too lazy to change it. So then I keep it like that. But this one I have to change it, huh? 5v1 minus 3v2. So v2 is going to be
Negative
One
of the
v2 is going to be 1 minus. Then 1 minus. And then 1 minus.
Yes. So minus 10.
It's going to be negative. And then you're going to have 40 minus negative 10 minus 50. So this comes out to be negative.
Isn't there a
Okay, so
negative?
now
Negative 3v2
the solution
equals
should be
negative
what?
negative
V1
plus.
plus, let's see here.
Oh yeah. Yeah, it should be. Yeah.
In other words,
I think you forgot
Ryan,
to
huh?
you forgot to distribute the negative.
So first, should for the V2,
Yeah.
the momentum should be negative 1 plus 5.
3v2 goes over there.
Yeah.
5v1
Minus one.
minus 1. Oh, okay.
But
This
do
is
they
what
change
happens
back?
when you make a mistake, and then when you're trying to redo it, you don't start scratch. You try to fix things. So don't do that on the test. Erase.
You can do it again.
Just start fresh, because you're bound to go back and screw it up. You know. Okay. So
But
then
then
what?
change it.
So
Then
does
done.
that change this?
Yes. That's
So then you're gonna have what? 25.
This is still same equation after you open.
Oh, but then when you square it, it doesn't
Yeah, it
change.
doesn't matter because of the one negative overall.
Oh, okay. Then we still stay the same answer.
Yes.
So what I'm saying is that V1, one of the answers for V1 should be 2. In other words, if these two blocks, oh no, sorry. One of the answers for V1 should be -1. Yeah, exactly, -1. In other words, if the two blocks come and they never actually make contact, it should still, that collision should still conserve momentum and kinetic energy. Even though the collision never happened, it's not a collision, you know. In other words, the passing of objects, you know, the passing of objects on the road that are on opposite lanes from each other, is that an event that conserves kinetic energy and momentum? Every time you drive on the road, there's another car on the other side coming the other way. Is there a collision happening? Well, not really physical, but is that event an event which is conserving momentum and kinetic energy? Yeah. So one of the solutions should be equal to the original scenario, right?
Really?
So if V1 was -1, it means they never actually collided. So this answer then should be factorable,
Oh.
and one of the solutions should be -1.
If it is perfectly elastic, one of them should be as the same
Yeah.
state as the original.
Yeah, which means the event where cars pass each other is actually an event that conserves energy and momentum.
I get different answers.
No, we actually do get that answer. V1 plus 1, isn't this factorable? -5 plus 4 is what?
Minus one.
-1. Yeah, it is factorable. So what is one of your possible answers? V1 is -1. Then what's your other possible answer? V1 is 5/4, 1.25 meters per second, which means, okay, the other solution is that they actually do make contact, and this one turns around, going back at 1.25 meters per second. You see? So that proves that you did it right, that all, you know, your steps are all right. So once you get the V1, you can substitute it into the V2 equation, right? So if you substitute that -1 answer, what's going to happen? Right? If you substitute the first of the answers, and then you put that there, you're going to get -1, -5, which is -6/3, which is -2. So V2 is -2, which means what? Well, it's going the other way, right? So the collision never happened, you see?
Oh, what does 6?
Huh?
It's 1.25 or 1.
No, I'm saying just to check if we did it
Oh.
right. Just to check we did it right. You get the answer that we didn't choose. You get the -1, and you should get -2, which is this original answer
Yeah.
also. The collision never happened. Right? So then, to get the true answer, you put the 5/4. Okay, so then you put V2 is -1 plus 5. So what is that here? -4 plus 25 is going to be 21/12. Get a common denominator, take the 4, put it over here. So then that's 1 9/12. which is 1.75, right? So that means this guy goes forward 1.25, this guy goes 1.75. Okay, which of the two blocks experienced the greater change in velocity? This block was going at 1, then it turned around, now is going back at 1.25. So how much change in velocity is that? 1 minus negative 1.25, that's 2.25. The velocity changes by 2.25. This one changed from 2 to 1.75, 3.75. So the lighter object experiences the greater change in velocity. Does that make sense? If you are driving a Toyota Prius and you get hit by a semi-truck, which car is going to bounce back and change velocity more? The Toyota, right?
So you don't buy smart.
Now, which car experiences the greater change in momentum, though? It should be the same. Because the overall change in momentum of the system is 0, right? So the delta P of the 5 kilogram should equal to the delta P of the 3 kilogram. So what is that? 5 times V final minus 5 times V initial. So the lighter car experiences the greater change in velocity, but not the greater change in momentum, you see? So 5 times V final is gonna be 1.25 minus 5 times the initial, which is negative 1. So that's going to be 6.25 plus 5, 11.25 kilogram meter per second. Okay? The change in momentum of the 3 kilogram three times V final, that's going to be negative 1.75 minus 3 times V initial, which is 2. Right? And 3 times 1.75, what is that going to be? 3 times 0.75 is 2.25? 5.25, right? Now this finally confirms that everything you've done is right? If the 2 you get is the same, then that matches, right? So negative 11.25. So the change in momentum of one block is the same as the negative change in momentum of the other block, right? Cool. So therefore, momentum of the system, the change in momentum of the system is 0. See? So now that we know how to do momentum collision problem, perfectly elastic, semi-elastic, and inelastic, we can say what are other cases, what are other kinds of problems where it's helpful to know about momentum and collisions. So those would involve problems that would include like a 2 or 3 part problem, where part of it would be to use the concept of momentum, you see. For example, what do I mean by that? So these are called combined problems. So let's say you have a block we can even put friction here. Let's say the coefficient of friction between this block and the surface is 0.2, and the coefficient of friction between this block and the surface is let's make this one 0.3. So the coefficient of friction between this block and the surface is 0.4. The coefficient of friction between this block and the surface is 0.3. So this is a smoother block, right? So now let's make this, let's say 5 kilograms, 2 kilograms. So we let this guy go, it comes down, right? It comes down, hits this one, and together they go down. Find for me the final velocity of the system when they reach the bottom. You see? So why is this a combined problem? Well, because you have to utilize your knowledge from previous sections, plus on top what we're learning about collisions and momentum, right? To analyze that.
So the connection is perfectly, perfect.
Yeah, they're sticking together.
So
So it's complete inelastic, yes, exactly. So then the problem might give you this height, you know, or maybe it gives you the distance. Let's say this is the same distance, 1 meter, 1 meter. So then what do I need to do? I need to find out the final velocity of the 5 kilogram just before it hits the 2 kilogram, right? So which method should I use to find the final velocity of the 5 kilogram? Should I use Newton's laws or conservation of energy work method? Well, this problem will be given to you on the next test, not test 3, which is Monday. Test 3 Monday is on chapter what? 6, 7, and 8, the energy chapter. On that test, if this problem arrives or something similar, you have to do with the energy method. Why? Because the test is testing your knowledge of energy. But when you get to test 4, you can say, I hate the energy method. I'm not going to do it the energy method. I'm going to do it the force Newton's law method, you know. So you could do either one just as easily for this one. And if it's on test 4, you're welcome to do it the Newton's law method, right? So how would you do it from the Newton's law? Find the acceleration of it, use kinematics, right? So you go in, all that to teach you that for Monday, make sure to do it with the energy method. There was a hidden message in that sentence. So with the Newton's law, you say mg sine theta minus mu kn is equal to ma. Right? Oh, the angle should the angle be given to you? Okay, yeah, let's get the angle. 40 degrees. And then what's n equal to? Mg cos theta, right? M cancel. So 9.8 sine of 40 minus 0.3 m cancels. 9.8 cosine 40 is A. So calculate the A. I like these kind of problems, because it brings together several chapters, you know, in one.
I do have a question.
Yeah.
So in this case, there's friction. So the momentum won't conserve if there's friction, right?
I think it does.
Oh, very good question. Okay, let's calculate this, then we'll get to that question. Yeah, very interesting question.
Yeah, that's why I'm confused a bit. So. 4.047. Yeah? Is that what you said?
Yeah.
Okay. Others are getting that? Okay, so once we get the A, we can find the final velocity. How? Well, if we're using Newton's law method, we're going to stick to that. We're not going to use kinetic energy or anything. So we're just going to do the final squared is V initial squared. This is probably the best one to use, right? Don't use the one that has a t in it, because it involves time. We don't care about the time here. Use the third equation of kinematics. That's the third equation. 2 times A times the distance that it's going is 1 meter. So then you're going to square root that. 2 times A times 1 meter. So that should be final. So something like 2 point something meters per second, right? 2.84 meters per second. So that's the final velocity of that 5 kilogram block just before it's going to hit the 2 kilogram block, right?
We're assuming the 2 kilogram block's not moving.
Yeah, probably somebody has their finger on it and then they let go. Somebody has their finger on the 2 kilogram block. Because you might say, why isn't the 2 kilogram moving, right? So you have to hold that. Then this guy comes. Usually when I see this kind of a problem, it's given to you in this wording. It says something like, a kid is coming down a snowy mountain while their sibling is sitting there playing with the snow, right? And as they come, they grab onto their sibling and together they go down. You know, so there's a real life scenario, right? So you go, hold on to your sibling and then together you go down, play with the snow. So then what's your final velocity, right? Okay, so now Jason's question is pretty insightful because he's asking, is momentum conserved? When this guy has a certain momentum and he collides with this, doesn't friction eat away from that, some of that momentum? You know? So it is a pretty question that's pretty thought-provoking and worth asking. Certainly if a 5 kilogram block comes and hits a tree, and that's the ultimate friction you can think of because the roots of the tree are so strong that it ain't gonna move anywhere, right? So if it comes, hits the tree, then it cannot transfer its momentum to that tree. So in that kind of case, its momentum is not conserved. But in this kind of a case where the friction is 0.4, it's not too much. Can it transfer almost all its momentum to that? Probably, you know. It's arguable, but since it's not that significant, you can kind of assume the momentum is conserved. Now, if the problem wants to give you more detail, it can say, assume 90% of the momentum of the 5 kilogram block is conserved upon colliding with the 2 kilogram block. Then you can, if it gave you more detail, you can certainly then calculate that. So that means 10% of its momentum is lost of the 5 kilogram block. But if you hit a tree, 100% of your momentum will be lost. You see? So just by that information, can you solve it? Yeah. Because once we know his final momentum, right? We can know it's the momentum of the 5 kilogram, right? Momentum initial of the 5 kilogram is going to be what? 5 times 2.84. 5 times its velocity that it has when it reaches there, right? So then that's going to be 0, 2, 40, 42, 4, 10, 14. And the units of momentum, kilogram meters per second. Right? So if 10% of that momentum is lost due to the collision with that guy and the little bit of friction, so then the total momentum at the end, P final at the end is going to be 0.9 of P initial. Right? Yeah. So then we can multiply that, and we're going to get 18, 1, 36, 37, 3, 12. Right? 12.78. Or the other way to do it is take 10% of it and subtract it from it, right? 1.42, yeah, 12.78.
Yeah.
You see? But if that piece of information wasn't given, you is going to assume that it is all conserved.
All concern? Oh.
If that information is not given, then you're going to assume that the momentum is conserved. Okay, then after that, what's going to happen? Now you're going to set that equal to their combined mass, because now it's a completely inelastic collision, right? So it's now combined mass. So then you're going to do 7 kilogram times V final. Because together, the 5 and the 2 has a mass of 7.
Yeah.
That's going to give you the final velocity right after the 5 hits the 2,
Yeah.
right? So then divide by 7.
1.82.
1 point
1.83.
83. Okay. So once you get the answers, fill in your picture. 1.83. Now that becomes your V initial of the 2-block system.
Yeah.
You see, so many steps here that you're going through. Then together, they're gonna go together. Now, how do I know they're gonna stick together? Notice I purposefully made the bottom one have more friction, right? If the bottom one has more friction and the top one is the smoother block, then they're gonna go together, right? If the bottom one has less friction and the top one has more friction, the top is gonna hit the bottom is gonna go by itself, right? They're not gonna go together. Then it's gonna be more like an inelastic, it's gonna be more like an elastic collision.
Yeah, elastic.
Yeah.
Can you explain this step again? Why did you divide the final momentum by 7?
Because the combined mass of the system, they're stuck together. So it's an inelastic collision.
Okay.
Yeah, so you say their combined mass. Right, so the momentum, the final momentum is equal to, you can say, show like this, 5 plus 2V final. You know? On the test, do that. The more you show work, the more you can check your work later when you're checking it. So show 5 plus 2, then the combined mass is 7. Then divide by 7, divide by 7. Okay, 1.83. So now, together, so how do we find the acceleration of the system now, if each one has different frictions? Now we gotta go back to chapter 5 problem, right? So if you have a block and another block, how do we find the acceleration of this system? And 2 times 9.8 times sine of 40, what's the friction? Mu Kn, right? 0.4 times n, which is 0.4 times 2 times 9.8 times cosine 40. 0.4 times 2 times 9.8 times cosine 40. Right, so it's basically chapter 5 is all over again. But then we have the 5 kilogram block pushing down on the 2 kilogram, saying, get out of the way, get out of the way, I want to go faster, right? So that force we can call P. So then what's going to happen? 2 times 9.8 times sine 40, 19.6 sine 40, minus 0.4, right? Minus 0.4 times the normal force, which is 2 times 9.8 times cosine 40. So this is its force, the gravity force down the incline, minus the friction, right? So mg sine theta minus mu kn, and then which direction is the p? The p is the top block pushing down on the bottom, so the p helps with this guy. So I have to add p to this. That's equal to what? 2A. Right? Now what are the forces on the top block? Now on the top block, the 2 kilogram pushes that up with a force of P. Right? So on the top block, the forces look like this. P mu K N 49 sine 40, and then 49 cosine 40, which is what we did here, right? Oh, you know what? We didn't do 49 because the masses we said canceled out. Okay, so now what are we gonna do? We're gonna do 49 sine 40 minus the friction, which is 0.3, right? The friction on the top block is 0.3. Times the normal force, which is 49 cosine 40. And then P is this time up. Minus P is equal to what? 5A. So ultimately, we don't even have to calculate the P, because if we add these two equations, the P's cancel. It's just an internal force between them, right?
Yeah. So you can see it as a.
You can see it as a system.
Yeah, as a
So ultimately, this doesn't really matter. All that matters is all the downward forces on the system, the weight, the friction on the system, and then the combined mass of the system. You see? So 49 sine 40 minus 19.6 sine 40 minus 0.4, 19.6 cosine 40 minus 0.3, 49 cosine 40 equals 7A. So it's a system. The downward component of the weight of gravity on both blocks, the friction on both blocks equals to the total mass of the system times A. So now calculate what the A is. Is it negative? Is it negative? Oh yeah?
Well, no minus. Is yours negative?
Yeah, but these two are positive. You know what? I did something wrong.
Yeah.
Why is this one negative? This plus this. Why is it negative? The two
Yeah.
downward components of gravity should be positive. The friction should be negative.
Right.
I was still thinking about the Man City's lost, I guess. I wanted them to win. Because the final with Man City versus versus Barca would be more interesting. Tottenham versus Barca, it doesn't sound right. Doesn't sound right. I don't know. But you know what though? It makes it good in a way to have surprises. 3.83. Okay, now once you get that, the other acceleration was 4.07. Once you get that, you'll do this step again to find out what their velocity is at the bottom. Two times right? 2 times 3.8, 3 times 1, right? From kinematics.
0.76. Also 2.77.
0.76
Oh, 2.77.
meters per second. So that's a good example of a combined problem. You have to do Newton's laws, then do the momentum collision, and if momentum is lost a little bit, then include that, then get the final velocity, then that becomes your initial, then recalculate the acceleration, right? And then do another problem. So it's quite a bit of pieces to the problem. Let's see another good example of a combined problem. Two of them is like good suffices to show you. How about this one? The 5 kilogram comes down, bounces completely elastically from the 2 kilogram, right? Bounces completely elastically. Tell me what height it goes up to after the collision and how much this compresses the spring. So assume the collision is perfectly elastic. So assume this height is 3 meters. Find H final and find the compression of the spring.
What's the coefficient for the spring?
Huh? The spring of the coefficient is going to be K, let's say 100 Newton per meter. So this one, are you going to do it Newton's law or more energy method?
Energy?
Yeah, see this one, even if it's after this test, you still will do it energy. Anytime you have got this kind of stuff going on with heights and springs especially, energy is better. So what am I going to do? I'm going to find the velocity of this guy, 5 kilogram. I can do it simply by energy, right? The potential energy initial equals to the final kinetic energy. So that's also the same thing as doing it by kinematics, just doing square root of 2gh, right? That gives you the velocity of the 5 kilogram just before it's going to hit the 2, right? So what is that? 6 times 9.8. Okay. Okay, now do the collision portion. Okay, for the collision portion, you can almost do it as if it's a horizontal problem. Imagine the 5 kilogram is going 7.67, and then 2 kilogram is stationary. They collide elastically. What's going to happen? Oh, you know what I should do? In order to make the problem realistic, I should put the 2 kilogram up here. Because if the 5 kilogram hits the 2, the 5 might continue just going down. All right?
Yeah.
So it's better to do the 2 hits the 5. It's not going to change the final velocity, Because the final velocity, the masses cancel.
Yeah.
See? But if 5 hits the 2, it's not going to bounce back up. It's going to come and continue going down with it. You know? But if the 2 comes and hits the 5, I think the 2 might bounce back, right? So how do we do that? We have to do momentum conservation and kinetic energy conservation, right? So again, 2 equations, 2 unknowns, because you got to conserve kinetic energy and momentum. See? So what's the momentum initial? 2 times 7.67. At least this one doesn't have momentum, it's 0.
Yeah.
See?
15.3.
15 point, what? 15.34, right?
Yeah.
How about kinetic energy? 1.5 times 2 times 7.67 squared plus 1.5 times is equal to 1.5 times 2 times v1 squared plus 5 times v2 squared. 2 cancels. And then you can do your substitution again. And then this is 1/5. Multiply everything by 5. You get 10. Multiply this by 5. And then expand this out, right? So this squared plus double the product. Oh no. This squared plus double the product plus this squared, right? Okay, so what did I tell you? It's gonna be a factorable quadratic equation, right? Whose one of the answers is what?
7.
The original velocity of the V1 was 7.67, right? So it's gonna be V1 minus 7.67. That's a great clue, So then what's the other one? 14 V1.
Let's see.
So what should I put here so that I get 352? So then you just divide 3.352 by 46.02?
40. What?
46?
Oh, sorry. Okay. 46.
Yeah, 46. Now just to check that I'm right, what should I do? Check the middle part, right? To see if the middle works. This times this, minus this times that, should give me positive. So 46 times V1, hold on.
Doesn't seem right.
Hmm?
I mean, it doesn't seem right.
No, it doesn't seem right. 14,
Oh, it should be plus.
Which
V1
one?
plus 7.67.
V1,
Since V1 is negative,
Oh,
so it
it's
should be plus. And the other one should be negative.
Because it's going in the
No.
opposite direction.
oh, because if V1 was negative,
Right.
then it would mean it was going, okay, perfect. So
Yeah.
this one should be plus, and
you
this
got
one should be minus,
Yeah,
but still, is that right?
that seems right.
7 times this is this.
Right.
Oh, negative 46 plus this, that might work, give
Yeah.
you 61.
Yeah, that's 61. That's it.
So negative 46 plus 7.67 times 14. 61.36, yeah.
Yeah.
Yeah, works. So then, this is your answer that you're looking for, V1. Oh, so that's pretty much. Wow, so this guy 2 kilogram comes, bounces back up with 3.28. You see, now we can say, oh, what height does it reach
Yeah.
after the collision, right? So we can do this step, but now so for the final height. So square root of 2 times 9.8 times h final is equal to v final, 3.287. You're just repeating this step, but reversing it. 3.287, now solve for h final. Well, square both sides and calculate h final. You know? So square this guy. Wow, 0.55 meters. It started with 3 meters. 3 meters is actually the height of the ceiling. Started from there. 0.55 meters is like barely like that, you know. Even though the energy, it was perfectly elastic, you know. Well, it gave some of its energy to this guy, right? So this guy now is going to go down. So how do we solve that part? What's the compression of the spring? So now what do we do? Well, once we get that, we go back and find V2, right? Put that in here, find V2, which is the velocity of the 5 kilogram, right? So take the V1 that you got, which is 3.287, and find the corresponding V2, right? So let's do that, 15.34 plus 2 times that's pretty fast. V2 4.3828. So now we know that the 5 kilogram is going down at 4.38 meters right after the collision. So then how much should the spring be compressed? To solve that part, I need what? Energy conservation.
I have a question.
See, not momentum conservation. Because this guy imparts its momentum to this guy and energy. But after that, energy takes over and says, okay, energy has to be conserved. So the kinetic energy of it changes to potential energy.
And what is HF?
HF is the final height that this guy bounces to.
Oh, bounce. Okay. All right.
Yeah.
Okay. Thank you.
Okay,
After that's after the collision, right?
Huh?
After the collision.
After the collision, yeah. And then the other one goes down. Okay, so then the 5 kilogram compresses, how much is that? The initial kinetic energy changes into final potential energy, right? So 1/2 times 5 times V squared is equal to 1/2 kx squared.
Oh, do we need to calculate the potential energy for the gravity?
Oh, he's saying, do we need to include the potential energy of gravity?
Because it
Did I forget that?
No, just for that.
So I'm saying the kinetic energy, this guy imparts kinetic energy to this, and then that kinetic energy changes to potential energy here of the spring. Do we need to include potential energy of gravity? He's saying it, but he's not sure. So
Yeah.
he wants backup from you guys.
Yeah, I'm not.
How many
sure.
of them do you need to support you before you are more sure? At least the SI coach, right?
Never mind. I should be sure. So sure.
You are sure?
Yeah.
So how would we include potential energy of gravity in there? What would we add?
We add to
The
beginning.
right side or the left side?
Left side.
Left side. And what do you say?
So because it go down, it transfer the potential energy of gravity to the potential energy of the spring.
Oh, so potential energy initial plus K initial.
Yeah.
So then you're gonna do what? mg
Except
h initial. So then what's the m? 5, 9.8. What's the h initial?
x.
X plus 5 over 2. The v initial is what?
4.38.
1/2 times 100 times x squared.
Yeah.
Is he right? Or do we add the potential energy on the right side? Or do we not add it at all? If we add it, it turns into a quadratic, right? I'm too lazy to do a quadratic today. Let's just not add it.
Just ignore it.
Because wouldn't that be X initial and not the compressed? How much you compress it? There are two different X's.
Yeah, so the original is right here, but we're assuming originally it's sitting uncompressed. It's just kind of sitting
Oh,
there.
okay.
So it's not compressed or stretched initially. It's just kind of sitting, and then this comes and hits it and bangs it, and now it starts compressing. So
Wouldn't the spring be canceling out?
I think we did do a problem like this back when I did, was it Monday or last week, where I did, I think I did do a problem with a block and a spring, guy. And I said, oh, let the block fall
Yeah.
and then compress the spring. Let's calculate how much the spring compresses.
Yeah.
I think it did end up being a quadratic equation.
But
Because after the block compressed the spring, it kept moving down, remember that? And as it moved down, its gravitational energy decreased and it converted into spring energy. You see? I think he's right. We do need to include it. The only time you don't need to include is if the block is moving horizontally and the block is on a spring. It hits the spring, it moves back, and the block goes this way, and there's only horizontal, right? In other words, if I turn this problem upside down, and I just go, okay, 2 kilogram block, 2 kilogram block is sliding on a flat surface, and it's sliding at this velocity. Oh no, it's sliding at this velocity, 7.67. hits this, it's gonna bounce back at that same speed, 3.28. And then this guy's gonna bounce this way. Then its kinetic energy converts into potential energy of spring. It has no gravitational energy to convert to spring energy, right? So the amount that this guy compresses is less than the amount that guy compresses. This guy, on top of the fact that this guy's hitting it, this guy's moving down with some kinetic, but it's also got potential. It's gonna go down further, right? Than if it's just horizontal. So yep, we need to include it. Now, which side do we include it? Can we include it on this side? Kinetic initial is potential final plus potential in the final, potential final of gravity, potential final of spring. Can we include it that side? Yeah,
negative.
but you gotta be careful. If you include it on the right side, that means you're gonna set your XY axis here. You're gonna say the initial gravitational energy is 0. When this guy hits this guy, it has no gravitational energy. As it's going down, the gravitational energy gets more and more negative. So that means this one here becomes negative mgx.
That means that once
Gravitational energy goes negative, the spring energy gets positive. But if you put the axis here, at the most compressed position, then the final gravitational energy is 0. So you have nothing here, but then the initial energy is positive. See? So it's your reference that matters. So if you add it on the left side, you add it positive. If you add it on the right side, you add it as negative. See? So he was right. So then we need to add here 49x plus this guy. So now it's a quadratic equation. Put that into solver and have it spit out the answer for you. And the answer? No. 1.59 meter, what is it? Yeah?
Meter.
Oh, it's just meters, right?
Yeah.
X. I wonder, we can quickly check our answer if we do like this. This collision was a perfectly elastic collision, right? So in other words, no energy lost to the collision. Whereas the previous problem we did, there's energy lost because the child is picking up the other child. It's an inelastic collision. Here, all energies are conserved. So can we say the initial potential energy that this block had, right? Initial potential energy that this guy had, what was it? 2 and 5. Right? So what was the initial energy that this guy had? mgh, right? Was it 3 meters?
3 meters.
So 6 times 5, 9.8, 58.8 joules. Should that energy be conserved? So at the end, when this guy goes down and comes back up, how much energy does it have at its highest position? How much energy does it have? Did we
Oh.
find the height that it has?
Yeah.
What was the final height?
Point
Oh yeah,
five
very
five.
little, right? Huh?
10.81.
7?
10.81.
10.81?
Yeah.
Okay. What other energies are there at the end? When this guy is compressed, how much energy does it, elastic energy does it have? What's the K? 100
100.
times the X squared.
Oh, 126.4.
What is this?
126.4.
So the total energy at the end is more than the energy at the beginning? So energy is not conserved?
The energy of the bottom block, the potential energy of gravity. That-
Oh, so should we include that, the potential energy of gravity?
I don't know.
Yeah, because when I'm saying the potential energy that this guy is initial, where with respect to what point is that energy? With respect to the top of this
You have
block?
to say-
3 meters.
Yeah, plus X.
Oh, yeah. So I have to count, since I'm counting this guy is compressed,
Right.
so I have to probably count all my heights from the compressed position,
That's right.
right? So maybe add another, what?
Plus X.
Plus X. So what's my X? 1.59. So
1.59.
add 1.59 to that. So 4.59. What I'm trying to see is if the initial energy is equal to the sum of the final energies.
Right.
Oh, but then if that's the case, what
That's
is
the
this
case.
height measured with
Plus-
respect to?
Plus 1.5.
No, that's
Yeah.
not good.
It's still plus.
Oh, it's all plus 1.59? So
Yeah.
what is this gonna be?
Yeah, that's not good. Okay, so that's 2 times that. And notice that like also 5 kg block has potential energy. In this case, mgh, since your like 0 point is 1.59 meters below. You
Yeah,
understand
so
that?
initial energy is, okay, so I have to count everything with respect to the bottom. This guy has energy, that guy has energy.
Right.
Oh, okay, so the initial energy of the 5 kilogram is gonna be 5 times 9.8 times what? 1.59. 2 times 9.8 times 4.59. Let's see what that comes out to. Because I want to show that the total energy of the system is conserved. Right? Hopefully.
Change that to
What
plus
should I change that?
plus 1.5.
Plus 1.59, right? So 1.59 plus 0.55, which is going to be 19.6 times. And then this one is the final energy of the spring,
Right.
1.59 squared. So this plus this is the final energy of the system.
Yeah, it's actually the same. It's about the same.
167.
Yeah, that's what I was.
160.
Oh my gosh, I'm getting a smile on my face.
7.8.
This is more exciting than Tottenham winning.
Yeah, 167.
Yeah, about the same.
Yes. Total energy conservation, baby.
Wow. So you can see at the whole system.
As a whole system.
Yeah.
Yeah. Here, since it's elastic collision, the total energy is initially, total energy is finally should equal. Okay, the other topic, the next one, I'm gonna skip over and say watch my extensive videos on two-dimensional collisions. So I do have plenty of videos, a block coming, another block coming, hitting each other, bouncing off at an angle like that. I do have videos and lecture notes on that. So those are collision problems that involve two dimensions, and it could be elastic and inelastic. So I focused on the one dimension. So now I'm gonna move on to center of mass calculations. How to find the center of mass of objects, which then will transition next week into finding the center of mass and also finding the moment of inertia of the object. How to calculate moments of inertia of different shapes. Center of mass, sometimes also called center of gravity, right? So how do you find the center of mass of an object? X center of mass Y center of mass, summation of Y sub I, M sub I, over summation of M sub I. And then you have the integral form of the equation. Okay. So suppose we want to use, first of all, this example. What kind of cases are there where I don't have to do an integral to find its center of mass? Then we'll focus on the integral ones. So the non-integral ones are where you have a system of objects that are connected to each other, whose individual centers of masses you already know. So they're a conglomeration of objects whose center of masses you know, but they happen to be glued together for the purposes of the problem. So for example, something like this. You have a sphere and then the rod. Let's say they're fused together at the ends. What's the center of mass of this system? It's like a club that they used to use in the caveman, right? So caveman. So what's the center of mass of that system? So if the individual masses of the two systems are given and their radius and lengths, so let's say this is a sphere and its radius is 2 meters and the mass is 10 kilograms, and then this is the rod, length is 5 meters and the mass is 8 kilograms. So where would the center of mass of that be? For spheres and cylinders, usually their radii are given. So just remember that their diameter is twice that. But for rods, their whole length is usually given. Not just from the center to the end, but the total length. Okay? So then what you do is you use this form of the equation, x center of mass, which is going to be x1 m1 plus x2 m2 over M1 plus M2. Okay? So then you decide where to put the XY axis, and then based on that, just like we did with that potential energy function, you decide the reference frame. So usually I like to do my reference the center of the leftmost object. That way I don't have any negatives to worry about. So I'm putting my axis right at the middle here, XY. So then X1 will represent the center of mass of the sphere with respect to that my reference. How far away is the center of the sphere from where I placed my origin? Well, I placed my origin at the center of the sphere so that X1 will be 0 on purpose, you see? So then this comes out 0. Then what's X2? X2 is how far away the center of the rod is from my origin, okay? So if the rod is a length 5 meters, its center will be there, right? So it's 2.5 meters. Right, from there to the end. So how far away is that from my origin? 2 plus that, 4.5. So X2 will be 4.5. Times M2, which is going to be the mass of the rod. So you're multiplying the center of that object from your origin times the mass of that object, right? And then you divide that by the total mass of the system, you see, which is your M1 10 plus 8. Uh, 8 times 4.5, that's going to be 4, 32, 36 over 18, right? Well, that's perfectly 2. Oh, so the center of mass is exactly right there. So if you put your finger there, you will balance perfectly, right at the edge of the rod, right? Now, what if you had placed your origin over here, at the left of the sphere? Could you have? Yeah. Then what would change? Then X1 would be the 2 times, right? It'd be, because the center of the sphere would be 2 meters, 2 times 10, right? So it'll be 2 times 10. But then, of course, this distance will change. From here to here is 2.5 plus 4, right? So that's a 2.5 plus 4, 6.5. So 6.5 plus 20 over 18. 26.5 over 18. No, did I do something wrong?
60.5 need to be times 8.
What did I do? I can't add that to it.
No, for the after one, the next one.
Okay, hold on, let me see. 2 times, I did 2 times 10, and then here I did 2.5, 4, 6.5 times 8. Oh yeah, I did that wrong. Okay, 6.5 times 8. That's gonna be 40, 48, 52, 72 over 18, which is 4. Yeah. So the point is still 4 meters away from where I put it. So how would you put your answer? You would just say the answer is at the edge between the sphere and the rod, really. That's just the best way to say it. And just to even point it out. Center of mass. Okay? Another way that you could apply this is any other kind of object where you don't necessarily have to integrate. You can even take, for example, the letters of the alphabet. So say, for example, these letters of the alphabet, the letter T, find the center of mass of that. The letter T, E, O, D, I. Some of them you have to do integral, the other ones you don't have to do integral. Like S, since it's a curved object, well, S is easy because it's symmetric. So the center of mass is going to be right there. T is going to be somewhere there, but yeah, T is a good example of not having to integrate because the shape is not curved. So let's do like F is another good example. F, T. So I'm gonna mimic my letter like that. Let's say that you have the letter F. It looks a little thicker on this side. Right? Next time you're like kind of gazing in class and a little bit dazed, and the teacher says, hey, wake up, what are you doing? You gotta be awake. Say, I am awake. I'm just thinking about the letters of the periodic table there, what the center of mass of the letter F is. You will be so impressing the teachers and everybody else sitting there. You got that made. I mean, the next test gives you extra credit. Extra credit. Right? Okay, so now let's say like this. I think this one is shorter. Let's say these two have the same thicknesses, but this one is longer. It's a nice F. Where's the center of mass of that? Right? So I have to give you the dimensions. Let's say 10 centimeters. It's a nice F, yeah. Find the X component of the center of mass of that and the Y. The X and the Y. Beautiful one. Do we have to integrate? No, because you don't have any curved edges. You don't have to do any integration. So you decide what your XY axis is, right? So then I'm gonna put my X axis like this. My Y axis along the left edge. Then you decide to break this up into a bunch of rectangles whose center of mass you already know. Okay, how can I break this up? Probably 3 rectangles, right? I'm gonna go like this, like this. This is my one rectangle. This is my second rectangle, and this is my third rectangle. So when I do X center of mass is X1, M1, X2, M2, then X1 will be the center of mass of the first rectangle. And see? After this, you will never look at letters the same way. Right? Then you're gonna start finding the center of mass of numbers. Where's the center of mass of the number 4? Right here. You know, God, turning you into nerds. 7. Okay? So now you just do what? What's X1? X1, well, let's write it down. M1, X2, M2, X3, M3. What's X1? X1 is the X component of the center of mass of the first rectangle. So it's gonna be right in the middle, right? What's the X component? So what I would do, just put a dot where the center of mass of each one is. Oh, you know what else it needs to tell us? What's the distance from here to here? It never told us that. Let's say 5. Right? It needs to tell you that. That's 5, 7, 5, 2, 7, 8, and this is 2. You know what? I think this should be 4. 4, 6. This is going to be 3. 4, 6, 3 is 9, 1 is 10. Yeah. Okay, so now what's going to be the center of this guy? X center of mass is going to be 1, right? So that's going to be 1. What's going to be its mass? Well, in order to know the mass, I would have to know the surface area density,
Yeah.
how dense it is. I don't need the mass, I just need the surface area because the material is the same material. It's not like this is bronze and this is silver and this is copper. If they're different materials, then I need their densities. But if it's same material, I don't need their density. So I just need this, the area of this. What's the area of that? 10 times 2, right? So just write out 10 times 2 so it's easier to check. Then the x2 is the center of mass of this guy. So that's going to be 1 unit here, right? 1 plus the 2. So it's a bit tricky. You have to make sure you're not making mistakes. 1 plus 2, that's 3. Right? You're always measuring from the y-axis. You see? So that's going to be 3. What is its mass? 2 times 2. Plus x3 is this one. So that's going to be, let's see here. This is 6. This is going to be 4, right? So that's going to be 2 plus 2, 4. Its surface area, 4 times 1. Right? Now divide that by what? The surface area is all added up. Right?
Yeah.
So 20 plus this is the surface area 4 plus the 4. So what do I get here? 20 plus 4 times 3, 12 plus 16 over
So
28.
I have a
Question? Yeah.
oh no, sorry, I make it wrong.
Yeah? 32. What is that? $1.71? Huh? Oh, so the center of mass in the x direction is actually inside of the this. I thought it was going to be in the air somewhere. It could be in the air, you know, but in this case it's actually in the letter.
It's 1 times 10 times 2. What does the 2 mean?
The surface area,
Oh, the surface
10 times 2.
Okay. Alright.
Yeah. See, that's why I wrote it out so that later when you check, you say, what does it mean, you know? I didn't write out 20. And this is 2 times 2 surface area. So I'm doing area 1, area 2, area 3. Area 1 plus area 2 plus area 3. The surface area of each one. Okay, now let's do the y center of mass. Well, see if you can do it. Start it slightly earlier than I do, and then I will start it. Do y1 m1 plus y2 m2 plus y3 m3 You guys got it? Like that?
Yes.
5 times 10 times 2. Right? The area doesn't change. Plus 5, 4 plus the 1, times 2, plus 6, 9, 9.5. 9.5 times 4 times 1. Okay? So let's see where that ends up.
5.64. 158 over
38.
158 over 38.
What is that?
Yes. 5.64.
Oh, 5.64 centimeters. So what is that? Oh, 5, 4. Oh, so the center of mass 5.64.
A little
This is
over.
5, so it's slightly over here. So this is the center of mass right there. What's the experimental way of finding the center of mass for this object? We're gonna do that in the lab, I think, next week's lab. The general way of finding the center of mass is tie it from 3 random holes. Drill a hole, tie it from 3 random holes. So if you tie it from here, right, which direction is it gonna be facing? Something like this, right?
Yeah.
That hole. Then you put a plumb line with a certain weight, and then draw a line across it. Right? Draw a line across the object. Then tie it from that hole, right? So how would that face? Like this, right? Plumb line. Heavy weight, right? Draw a line across it, but it already has that other line, right? Okay, 2 lines wherever they cross, that's the center of mass. But just to be sure, you do a 3rd hole, so make sure that the 3rd hole also crosses through that line. Make sure you didn't do any mistake. Right? If 3 lines cross at the same point, that confirms that's the center of mass. So in our case, it's gonna cross over here. All points of gravity cross through the center of mass. Nice, okay. Well, topics changed quite a bit now, huh? Now that we're at center of mass, so next Wednesday we'll continue doing more of that and moment of inertia. Okay, Monday is our test. Chapter 6, 7, 8.